Thanks. Apparently not everybody's back yet from the tour, so let's hope it's going to fill up a bit more. The first talk is going to be given by Will Mandel on action conditioned tactile prediction.
Maybe. Oh. Okay. Is it playing? Yeah. Okay. Hey everyone. I'm Willow, and this is my work on action conditioned tactile prediction with a case study on slip prediction. Okay. So tactile sensation is often applied in a reactive manner. For example, when dealing with object slippage, projects often generate binary slip signals from tactile data, classifying with a tool like random forest, and then when slip is detected, you increase the grip force on the object. And that works really nicely, but if we can perform tactile prediction over time horizons, it will enable proactive control within the same scenes, giving us a greater range of control techniques and potential solutions that we can apply. In the case of slippage control, that might mean not increasing the grip force because the object's delicate or we're already at max grip force, and instead doing more appropriate control with joint space trajectories or adjusting the grasp position on the object. And although some researchers attempted to perform tactile prediction before, these projects were very application focused and they didn't provide us with any insight into the tactile prediction problem itself, only in how to use it afterwards. So in our work, we did a comparison study between different unsupervised learning models applied to pick and move motions, and we further explored prediction models within the context of a slippage prediction application, where we try to work out if and when slippage will occur during a pick and move task. So on the left-hand side, or my right-hand side, is an example of the pick and move trials that we were performing in our data collection. And on the left-hand side is the tactile frames during this pick and move. And as you can see, it consists of just lifting up the object and moving it around and creating some slippage. And we created these motions using pseudo-random teleoperated motions from humans, where we basically said, can you create as much slippage as possible? And it occurred in around 10% of the frames in our data set. So we used a low-resolution magnetic-based tactile sensor called the Zeller U-Skin, which takes shear X, shear Y, and a normal Z force. We also stored in our data set the robot states, so we could actually condition our model. And finally, to test, I'm not sure what's going on there. And finally, to test slip prediction, we also attached the Aruco markers to the side and top of the object, which allowed us to classify when slippage was happening by thresholding on the yaw values. The data set in total was 52 trials for training and then 22 trials of unseen objects for testing. So to compare and contrast our possible key features that we might apply to tactile prediction, we analyzed the prediction performance on the state-of-the-art tactile prediction models like Pixel MotionNet, as well as some simple benchmarks like MLPs, and some video prediction algorithms like CDNA and SVG, as well as developing our own models in the setting, which we called action-conditioned tactile predictor, and a video version of the same one, action-conditioned tactile video predictor. So within the comparison study, we showed that our model ACT-VP, the video predictor, worked best with respect to like standard performance measures, but what we found was that when we did qualitative observations of the plots, we found that their indications weren't very realistic, and we found that our linear-based models, ACTP, performed much better predictions that were both smoother and predicting tactile changes ahead of time, like you can see on the bottom here. We also found that, I mean, naturally, at the beginning of the system, we're not able to predict these changes in tactile behavior. That's when the grasping is happening. So we don't provide any like visual information about our object. So the system's never going to be able to predict the picking. It's just the motion afterwards. So when it comes to slippage, to generate the slip predictions, we use random forests on the predicted horizons of our tactile systems, producing a slip classification at just t plus 10. The performance metric we used was a combination of both the slip percentages that were picked up in the data set, but also how close the slip instances were to the ground truth. On the right here is a nice example where we see the tactile predictions and then the classifications to slip during a 15-second pick and move trial. Yeah, finally, we found some interesting features. Like, for example, we found that the video-based prediction networks actually had a negative impact on tactile prediction, and there was a variety of other features that we found counterintuitively weren't helping. So in summary, what we found was that our comparison technique showed that our model was the best performing model in the data sets. We further compared this on a tactile prediction, slip prediction task, and one of the key limitations of our work was that we only tested on flat surfaced objects, so we thought for future work we're going to try to do predictions with non-flat surfaced objects. Thank you very much.
Next up, we have Shupeng Xu, who is going to tell us more about sample-efficient grasp learning using equivariant models.
Thank you. Hello, everybody. My name is Shupeng Zhu from Northeastern University. Today, I'm glad to present our work, Sample-Efficient Grasp Learning Using Equivariant Models. It's a joint work with Dian Wang, Andre Bizarre, Guang'an Su, Robin Waters, and Robert Platt. So grasp detection is an important trend in robotic grasping, which utilizes machine learning to train a neural network Q that is able to infer the grasp pose and the position A from an image observation S. So the current grasp detection method is able to learn a good grasp function and generalize to novel objects. However, they suffer from low sample efficiency, which typically requires millions of grasp samples or hundreds of robot hours. Moreover, some of the methods use simulated data suffer from the scintillator gap. That was due to the simulation dynamic mismatches the real-world dynamic. So for our method not only able to learn a good grasp function and have the generalization ability, but also boosts the sample efficiency by orders of magnitude, so that we only require hundreds of grasp samples or equivalently 1.5 robot hours. Such high sample efficiency enabled us to train from scratch on a physical robot, therefore overcome the scintillator gap or potentially the uniqueness of the robot hardware. So the core discovery is that we found the grasp function is equivariant. Let's take image S for an example. Through grasp function f, we obtain a grasp pose A. Now, if I randomly translate or rotate the image S by G, the grasp pose will be translated and rotated correspondingly. This indicates that the grasp function is equivariant to translation and rotation, as denoted by equation 1. So what we do is we enforcing the equivariance using equivariant neural network. Therefore, for network Q, it inherits such equivariance property. So what is equivariant network? It's a network have a set of the convolutional filter that not only translates, but also rotates. Therefore, once the network learns a set of the convolutional filters for image S, it automatically generalizes to any translated or rotated image GS, as shown in this slide. So once our grasp function Q learns the grasp pose in this image state, it generalizes to any translated and rotated images. Notice that we only use the depth image, for it is sufficient to learn a good grasp function. And besides this, we also use the method called ASR to reduce the complexity of evaluating the entire action space. So we have a two-stage inference. First, we use Q1 network to evaluate the translational actions and select the translational action. Second, we take an image crop centered at that selected action and feed it into the Q2 network. Now, the Q2 network evaluates the rotational actions. So for Q1 network, we choose default equivariance, and for the Q2 network, we choose C16 equivariance. So as we said, we train our method completely from scratch on the physical robot. The training set includes 15 objects. Testing set includes novel 15 objects. The left video shows the training process and the testing process. As you can see, at the beginning of the training, the robot just performed random grasp in the tray. It's about 20% success rate. And after a while, roughly an hour of the training, it achieved 80% success rate. And at the end of the training is about 90 minutes. We tested it on the novel cluttered objects, and it achieved 95% success rate. The right figure shows the learning curve. The x-axis is number of grasps ranging from 0 to 600, and the y-axis is the success rate. Our method, denoted by color blue, reaches much higher sample efficiency. Yeah, feel free to ask any questions in our poster session. And our code is open sourced. That's it. Thank you.
For the third talk, we're going back to tactile sensing, presented by Joe Huang on understanding dynamic tactile sensing for liquid property estimation.
Hello, I'm Hongrui Huang. For robots to operate in our households, they need to be able to perceive common objects. One common class of object is liquid, such as sauces, drinks, detergents, and so on. In this video, by shaking the container, human can use tactile sensing to quickly answer questions like how much liquid is left, how viscous the liquid is. We want to enable robots for such an ability. When we interact with a bottle, different liquids will have different movements, which is caused by the liquid properties. In this work, by interacting with the container, we want the robot to infer liquid volume and viscosity in the container using only tactile sensing. A common approach is to learn to predict liquid properties using the tactile patterns in a purely data-driven way. However, these data-driven approaches often require a lot of data and suffers from low accuracy. Another approach is to build a physics-based model by analyzing the fluid dynamics of the liquid content. However, their model is limited to cylinder containers with precisely known dimensions. Our approach complements the data-driven and physics-based approaches by modeling the principal liquid dynamics using simple physics and learning the complex unmodeled dynamics in a data-driven way. We call it a physics-inspired approach. When a resting container is perturbed, the surface of its liquid content will oscillate and gradually decays away. When analyzing the system energy using the principle of working energy, we can see that the system oscillates because of the energy exchange between the kinetic and potential energy. The oscillation decays because the liquid's viscous force acts like friction and gradually dissipates the system's total energy. We therefore derive that the system is a second-order system. The takeaway of this model is that the decay rate is governed by the liquid viscosity, and the oscillation frequency is governed by the liquid surface height. In our method, the gripper first grasps the bottle with 2 gel-side tactile sensors and make an impulse movement. We collect the dynamic tactile signal in a free oscillation period. We track the markers of gel-side, extract the tactile data, and fit it with a damped oscillation signal. As the physics-inspired model suggested, the decay rate lambda and the oscillation frequency omega of this damping signal are highly relevant to the liquid viscosity and liquid surface height. We learn this relation in a data-driven way because it is affected by the complex shape of the container and the unmodeled dynamics. We take multiple experiments to prove our method. First, we'll try to classify 3 common liquids: water, oil, and detergent. Their viscosities are different, leading to different oscillation decay rate lambda, which can be perfectly extracted by our method. We achieve 100% classification accuracy for water, oil, and detergent, even without fixing their weight and amount. In addition, the model can be trained with only 24 data points, showing that our method is super data efficient. Secondly, we target a liquid with smaller differences, the sugar water with different concentration and height. We train a Gaussian process regression model using lambda and omega as input and regress the sugar concentration. We achieve a concentration regression mean average error of 15.3% and log viscosity prediction MAE of 0.16. It shows that our method can estimate the concentration of sugar solutions by only tactile sensing. We use the same dataset and method to regress on the liquid height. We achieve a high regression MAE of 0.56 millimeter, which is near the limit of the ruler's precision. Additionally, the same model can also be used to estimate viscosity and height of unseen liquids such as marine. We also show our method can be generalized to different containers, such as a large cuboid container on the left and the cylinder bottle on the right. In addition, the model can be transformed between different containers. Based on the trained model of the groove cuboid container and some limited amount of fine-tuned data on a new cuboid container in a different size, we can fit a model for a new container. With only 15 fine-tuned data, the tuned model can predict well with the concentration prediction MAE of 19.3%. To conclude our work, we propose a physics-inspired model of the liquid container system for dynamic tactile sensing. Based on this, we achieve liquid viscosity and liquid height estimation. We also show our method can be generalized to different liquids and different containers well. Thank you for watching, and I'll see you at poster 17.
The final presentation in the first block before the Q&A is going to be given by Griffin Tabor on adaptive manipulation of conductive non-magnetic objects via a continuous model of magnetically induced force and torque.
It's a bit of a mouthful. Hi, my name is Griffin Tabor, and I'm here to talk about our recent paper, Adaptive Manipulation of Conductive Non-Magnetic Objects via Continuous Model of Magnetically Induced Force and Torque. Our research builds on using eddy currents, enabling us to produce force and torque on conductive objects, which, while not unknown, manipulation with these effects is relatively unexplored. In a nutshell, it works by moving a magnetic source and a conductive object relative to each other. This produces current on the conductive object, creating a small magnetic field that then interacts with the original magnetic field. Specifically, we think this type of manipulation will be especially effective at cleaning up the thousands of pieces of space debris that we have left in space over the last few decades. These pieces are largely aluminum and titanium and tumbling in haphazard orbits. Classical techniques of manipulation are ill-suited because the object motion would be dangerous to a physical manipulator. We recently published work where we categorized the force and torque produced when you rotate a magnetic dipole source near a conductive object in 3 different configurations. With respect to the vector between the magnet and the object, these configurations are parallel and anti-parallel, shown as the green and blue arrows, or orthogonal, shown as any of the red arrows. We fit this new novel model and put it into wrenches in the world frame to get these 3 actions. The model shown previously, however, is not invertible. To use it in a controller, we need a way to map desired wrenches to control actions. This turns into an optimization problem across each magnet and each action, selecting optimal continuous values subject to bound constraints. Here we show 6 magnets in simulation manipulating a sphere in 6DOF. Recreating these experiments with physical experiments is not feasible. We wanted a frictionless zero-gravity simulation. Instead, we simulate zero gravity on the surface of water and physically demonstrated manipulation in 3DOF. For this work, we try to fill in the gap in our previous model, supporting arbitrary axis of rotation. We define theta to be the angle between the axis of rotation and the vector pointing towards the object. In this framework, the old model was theta equals 0, 90, and 180 degrees. We collected data at different values of theta using similar methodology to previous work, a combination of benchtop tests and FEA-based simulation. Looking at the data, we see a clear sinusoidal trend, with the largest in the rho dimension, which is the axis pointing towards the object. We take the value of the old model at its 0, 90, and 180 degree positions and use simple trigonometric functions to interpolate them. Given a vector rho between object and magnet and a dipole rotation axis omega, we can rework our model from spherical coordinates into some end effector frame. To go with the new model, we need a new updated control optimization. Previously, we independently searched over each magnet and each mode. The new continuous model allows us to search over an entire magnet's control space, in this case, psi and z, to select the unit vector omega, as well as dipole strength. Up until this point, we have focused on modeling known spherical objects and manipulating them. But the goal is to move towards real, arbitrary objects. Given data from a manipulation experiment, we can perform system identification to identify the object properties that best explain the observed motion. We use the same force-torque model we use in our control optimization to create a simple least squares optimization problem. Additionally, we solve the same problem online. Our adaptive controller, building a local dynamics model, enables us to fit our model of spherical objects onto objects that could never be globally modeled as a sphere, and use our adaptive control on spheres and non-spheres alike. It is also interesting to note that all 4 objects here were initialized the same, as a small copper sphere, and the PID gains and PID controllers are identical for all of them. The difference between them is captured in the model adjusting the current estimated object size, shown here as ghost objects. So in conclusion, we expanded the modeled region and removed the discrete components. We introduced adaptive control to allow manipulation of unknown spheres. And we demonstrated the first non-spherical object manipulation with eddy currents. We're at poster 18, happy to answer any questions.
Yeah, I can stay up here for the Q&A. Let me just go grab the mic. Any questions from the audience or online? If not, then I'll just kick it off with a question from my side. So for Will, first talk. I was wondering how specific your method is to the tactile sensor you're using, and if that would make a big difference if you swap it out to an optical one, for instance.
Yeah, I think it. Hello, hello. Yeah, I think it would make a big difference. I think the low resolution of our tactile sensor helps us in our scenario because we're using flat objects. So it's a low resolution problem. But as you start to test on more varied objects, like I think of like Lego brick style nodules on the end of the object, I think you'd have to use a more high resolution sensor like an optical tactile sensor.
Great, good. Still no questions from the audience. Good, then I'll just continue with a few more. For the equivariant models, so I mean the obvious question is, why is it better to embed that in the network structure itself rather than just doing a whole lot of data augmentation by rotating the images and shifting them?
That's a good question. Actually, from the baseline comparison, all of the baselines have selected from the extensive different data augmentation parameters, but still our method outperform. A simple question for it is, the data augmentation only can guarantee the equivalence in the data you have experienced, but it not guarantee for the unexperienced observation or new objects. But the equivalence model can guarantee such equivalence in even unseen objects.
Okay, thanks a lot. Finally.
Yeah, so I had a question for the grasping and determining viscosity and fluid levels. And so I'm curious because the videos you showed sort of had it grasping in the same position, the bottle's in the same position. So if I grasp the bottle upright, would you have to sort of train a new model for that sort of orientation? And I guess, are there ways to maybe sort of extract like more fundamental information, so any way I grasp a bottle, I would still be able to figure out?
That's a good question. So first of all, like if you grasp it upright, like the oscillation is not like obvious enough for the tactile sensor to really grasp that, to really capture that data. So that's why we grasp on the horizontal direction. And technically, like we didn't. Every time when we put the bottle in between the fingers, like they're in slightly different locations, so we're never like trying to make it exactly the same position when we're doing our experiments. So like, but it still have to be around the center of mass, otherwise it might slip away. So it's just like some constraint that like inherently we made.
on this side, please.
Yeah. I have a question for the last talk. Really interesting talk. It's a really interesting problem. It's going to be a really important thing to address. How do you feel like the magnitude of the forces that you're using for the manipulation relate to the sort of ambient magnitude of dynamic forces happening in the magnetic realm in that region of the Kessler belt?
Yeah, so the easy answer is that the force is actually decaying so much with distance, no one else's effects are going to dominate the system. So we would be the largest magnetic field relative from the point of an object's perspective. There is questions of the amount of force we can produce that are important, which is not very much. The video is at 20x speed. These experiments are 40 minutes to draw a square in our tub of water. But the idea is that if an object is spinning haphazardly, there isn't really an alternative of how you grab it. So,
thank you.
Good. And then last question.
Yeah, I have a question for the third paper. Really cool work. I'm wondering, what's your intuition on extending that method to other type of tasks? For example, rigid objects, or the similar methodology applied to other kind of tasks.
So that's a good question. So I think the main takeaway of my project, our approach, is that we divide the approach into a physics-based and a data-driven. So it's a combination of both. So I think one thing that I really want to deliver is the message that in order to do that dynamic tactile sensing, it will be a good idea to kind of understand what you're trying to estimate. And it shows in our approach, for this specific task, if you understand that, then you can actually do pretty well, much better than just simple data-driven or simple physics-based. So you kind of need a thing from both worlds, because tactile sensing isn't that repeatable, and you need to know what you're trying to know. That's what my belief is. So hopefully that is but specifically this model, can it generalize to solid content estimation? Yeah, probably not exactly this model, but you can build another model, and we are also trying to do that in our group.
Got it. Thanks a lot.
No problem.
Then let's give all the speakers another big round of applause. And we can start the countdown for the last 4 presentations of the conference. The first of those is going to be given by Ed Bray on distributed optimization and deconstruction of bridges by self-assembling robots.
Hello, so my name is Ed. I'm from the University of Sheffield, and this is work that I did with my supervisor, Roderick Gross. So we consider swarms of robots, which are large groups of robots working together to accomplish one task. These tasks tend to be tasks which cover a large area, so these robots can spread out, or ones which require redundancy. So if a couple of robots break, the whole task can still be achieved. Typically, these robots are quite small because they have to be quite cheap to manufacture a lot of them, which has a few advantages, like you can imagine they can squeeze through small gaps, but other obstacles are much harder to overcome. This work focuses on how they can overcome, how they can cross gaps in the terrain through self-assembly, inspired by ants, as shown on the left, and sort of encouraged by previous work in this area. But we take a different approach to the one seen there. So we consider a 2D grid of agents who build a bridge between these two vertical fixed support surfaces. In work published last year, we focused on part 1 of this problem, which was building a cantilever. So incrementally building the structure in a force-aware way so that it won't collapse. We use this as a starting point for the work in this conference, which focuses on 2 novel problems. So from here, agents can become active, as shown there, and they communicate with the agent above, which tells them the moment and the axial force in its links. We calculate criticalness from this, which is how close that link is to failure. The robot moves around the structure like this, and it can also pass through into the 3rd dimension to travel between the top and bottom surfaces. Using this framework, we consider 2 novel problems. So we first consider, once the other side of the bridge of the void is reached, we can maybe lose some robots and they can do something else on the other side. We call this optimization. So it's reducing the number of robots in the structure while maintaining stability. We also then consider how you could deconstruct this structure, again, while making sure it doesn't collapse. We do this by first extending and building a strong structure, and then deconstructing column-wise. We'll look at this optimization problem first. So there's only time for a really quick overview here. But basically, agents switch between a few modes. So they start off as placed, and they become active in the releasing mode based on how much force is in their links. At this point, they move underneath the structure and gather data as they go, and eventually, if they believe the structure is stable, they will leave it. But if they believe the structure is unstable, they'll try and place somewhere depending on the force information they've reached. So they try and place somewhere probabilistically near an area of high force. If two agents are traveling in opposite directions and can counter each other, they just swap information and like become one another because it's a homogeneous group of agents. This is best shown with a video, which we have here. So on the left, you'll see robots moving around, and the links between them are colored by the criticalness, like the force in the links. And on the right, there's like an overview of the moment in the force throughout the structure. So this agent has become active, and it will first travel to the left, and here it's swapping with another one that's trying to go to the right. So eventually, one of these agents will reach the right-hand side, and this agent has decided that the structure is stable, and it can leave happily without causing the structure to collapse. This continues until eventually one of them decides the structure is unstable, and you see it places there to try and reinforce it. So we have this like trade-off of agents placing and moving around. If an agent releases but makes the links around it critical, it places back where it was. And this continues until 50 steps pass without any change. And then we've reduced to 26 agents there from about 100. Now we'll talk about the second problem, which is deconstruction. So it's similar to before, but we have one new mode called force releasing, so agents can tell each other to release if they need to. Gathering agents enter the simulation above the right-hand side, as shown there, or they can release as before. And they place, depending on whether they believe the equivalent unsupported cantilever is stable, which is the region shown there, which basically means like if the agent left of that was released, would that cantilever be stable? And this, we calculate this by augmenting the force information using some elastic beam theory from civil engineering to calculate this. Again, this is best shown with a video, which we'll play in a second. So agents add themselves from the right-hand side, as shown, and this one will move around. When it gets here, it will release the one on the left of it because it believes that equivalent unsupported cantilever is stable. So now you can see agent 23 will release itself, and then continue like this. And agents can release as before on the left-hand side there. So again, agents are like adding themselves and also reconfiguring from the left to build a strong structure. And eventually, one of the agents decides that it's safe to release that agent 0, and then the structure would deconstruct column-wise after that. Yeah. Cool, so that's all we really have time for in this presentation. There's a lot more in the paper, including some calculation of optimal bridges and some conflict resolution, and also like an analysis of a maximum momentum force. In future, we hope to implement this on real robots. I know people are crying out for systems in this paper, in this conference, so I've got a system here, which I'll be showing off at the poster session later on. Thank you.
The next talk is by Lasse Peters on learning mixed strategies in strategy games.
Hi, my name is Lasse Peters, and I would like to present to you our work on learning mixed strategies in trajectory games. Dynamic game theory, which is the focus of this work, studies the strategic interaction of multiple players with individual objectives over time. As a running example throughout this work, we consider the game of tag, for which you can see a real-world example here. This kind of problem is particularly interesting since competitive play in this scenario requires players to maintain a level of unpredictability. To highlight this challenge, we consider a simplified model of the tag game played between the point mass pursuer and evader with positions constrained to a polygonal region. This problem can be cast as a coupled optimization problem in which the objective of the first player, the pursuer, is to minimize the distance to their opponent while the evader seeks to do the opposite. A key challenge with this formulation, however, is that it only considers deterministic behavior, which may be exploited by a competitive opponent. For example, consider the scenario shown on the right. If here the red pursuer can predict that a rational evader would go to the top, they could chase them down into that corner. And to address that challenge, the goal of this work is to compute strategically randomized, so-called mixed strategy solutions to trajectory games. To this end, we propose a lifted formulation of trajectory games in which players now optimize their expected cost by choosing both the weights and the support of a categorical distribution over multiple trajectory candidates. And at runtime, players sample from this optimized distribution to minimize their expected cost. You can see an example of such a lifted strategy on the right, where now the evader randomizes between either going left or going right, and thereby also forces the pursuer to consider multiple options. While this formulation does indeed admit non-exploitable solutions, it unfortunately also introduces a computational challenge, since it drastically increases the problem size. And therefore, the second contribution is that we propose a novel computational method to solve these lift games efficiently. The key idea behind our approach is that for given trajectory candidates of all players, we can rapidly compute the equilibrium mixing weights Q by first evaluating each player's cost for all possible trajectory combinations and then solving a bimatrix game over the resulting cost matrices A and B. For the resulting equilibrium mixing weights and cost matrices, we can then directly compute the expected cost for each player. And the key insight underpinning our method is that this entire computation is differentiable. In particular, we show that a bimatrix game can be differentiated efficiently. We use this gradient information to train a trajectory generator for each player, which predicts competitive trajectory candidates for given game configurations. And by embedding a differentiable trajectory optimization layer in each of these generators, we further ensure that the generated candidate plans remain feasible throughout the learning procedure. The resulting structured learning policy admits inference and gradient computation within milliseconds on a standard laptop. To demonstrate the effectiveness of this approach, here we show our method learning from scratch in receding horizon self-play for the tag game. Within only 2 minutes of training, we are able to learn highly competitive mixed strategies for this problem, for both players. So we perform a range of evaluations of this method, for which I would like to highlight the following main results. First, when comparing against the baseline, which uses sampling to discretize the game, we find that such an approach requires many samples to match the performance of our learning-based method. Further, in decentralized head-to-head competition, we find that lifting provides a competitive advantage over non-lifted formulations of the tag game. And finally, we also obtained preliminary results which demonstrate that our method scales even to many player general sum settings, like the 10-player collision avoidance scenario shown on the right. So to summarize, the main takeaway of our work is that we enable the efficient computation of mixed strategies for competitive play by combining differentiable games with trajectory optimization in a structured learning framework. For more details, please come see us at the poster. We have poster 20, or visit the project website below. Thank you.
Next, we'll hear from Marcus Pereira about decentralized safe multi-agent stochastic optimal control.
Hi, everyone. My name is Marcus Pereira, and I'm going to be presenting a new framework for safe and decentralized multi-agent control. Suppose we have 8 agents starting on a circle, an obstacle at the center, and the goal is to swap positions with the diametrically opposite agent like so. Now, if more than 2 agents simultaneously try this, it could lead to unsafe behavior. And therefore, the agents must learn to perform this task in a coordinated fashion, which in turn requires safe exploration. This is an example of safe behavior, but it requires an agent to be safe with respect to all the other agents, and for all agents to be safe with respect to the obstacle. We refer to this as the centralized approach, in which the agents are in consensus by default, but it does not allow reducing constraints or parallelization. So instead of trying to be safe with respect to all agents, let us only consider safety with respect to the most immediate neighbors. This allows for a drastic reduction in the number of constraints. Now notice that the pink agent actually belongs to 3 different neighborhoods, and that leads to a coupling of decision variables across the neighborhoods. To decouple them, we introduce copy variables, which are the ego agent's opinions on what its neighbor should do. Decoupling the neighborhood problems now allows for parallelization, but this comes at a cost. For instance, we could have agent orange's opinion, pink's opinion, and green's opinion on what agent pink should do. Now, in order to stay safe, they must agree on a mutually safe action. So the benefits of decentralization are reduction in the number of constraints, parallelization, at the cost of having to establish consensus. Now, formally, we aim to minimize this expected cost, which consists of a terminal cost term and a running cost term over a fixed time horizon, capital T, which is subject to the stochastic control affine dynamics of the system and a collection of user-defined safety constraints. This is a stochastic optimal control problem, and it is well known that it leads to the Hamilton-Jacobi-Bellman PDE, whose solution yields the value function. Now, solving this PDE directly is known to suffer from the curse of dimensionality, and we therefore adopt a recently developed scalable approach that uses FBSDEs, where the forward SDE is simply the dynamics going forward in time, and the BSDE is governing the value function going backward in time. Now, notice that the terminal cost is simply the terminal condition, and the running cost is the drift term of the backward SDE. The safe and optimal control is obtained by solving the following constrained QP, where safety is ensured using stochastic control barrier functions. Now, backpropagating these BSDEs are notoriously difficult, and therefore this deep FBSD architecture that we adopt parameterizes the unknown value function at the initial time with trainable weights. An LSTM network predicts the gradient of the value function fed to a safety layer, which computes a safe control to forward propagate the system. And this is also used to forward propagate the value function. Now, we repeat this at every time step, and this is the unrolled compute graph. Finally, a loss function that compares the true and predicted terminal value is used to train the network. Now, the safety layer, one way to implement it is to solve the local neighborhood QPs in parallel in an inner loop until convergence, and then use consensus ADMM in the outer loop to solve for the consensus problem. But instead of this nested structure, we propose merging both the loops and solving both the problems in the same ADMM cycle. For this, we adopt the OSQP solver. The advantage is that each step is much cheaper and the overall algorithm is much faster. So presenting some of our results, the first task is along the same lines as the motivating example that we saw earlier. On the left-hand side, we see a single batch instance out of a batch of 64 instances. The goal there is to highlight that we ensure safety throughout the entire training process. And on the right-hand side, the agents are shown as point masses to show a distribution over the batches. Now notice that as iterations progress, the agents stop drifting away from the initial circle, and a coordinated turning maneuver begins to emerge. On the right-hand side, we see that the same policy is able to control an ensemble of trajectories, showing robustness to noise and completion of the task on average. Next, we consider an unsymmetrical version of the same task. In spite of an unsymmetrical distribution of the three obstacles, the coordinated turning maneuver is successfully learned. In this task, there's a moving obstacle that the agents have to avoid going from the bottom to the top. The moving obstacle cannot be controlled and is an example of an uncooperative agent. In spite of this, the agents learn to both dodge the moving obstacle and learn the coordinated swapping maneuver. Here we see the final performance of a task where agents are able to squeeze through a bottleneck and get into a desired formation on the other side. And this is an application of our framework to a large-scale formation task. So in conclusion, decentralization helps in drastic reduction in the number of constraints, so much so that for large problems, the centralized versions of those problems don't even fit on a single GPU and are very slow. Thank you so much for your attention. Please stop by our poster.
And the very final talk of this conference is going to be virtual by Lillian Clark on PropEM-L.
Hello, my name is Lily Clark, and today I'll be presenting our work on radio propagation environment modeling and learning for communication-aware multi-robot exploration. Connectivity is a key component of multi-robot exploration, especially in harsh remote environments where data needs to be transferred to a human operator. For example, our experiments consider 3-wheeled robots, 3-legged robots, 1 base station radio, up to 13 static relay radios, and about 1 hour of exploration covering hundreds of meters. Predicting signal strength of a point-to-point link, for example, from a robot to another robot, to the base station, or to a relay radio, is useful for communication-aware decision-making by the robot. Extending this prediction to build signal strength maps is useful for operator situational awareness and strategic planning. Radio signal propagation is a multi-scale process. First-order models are a linear function of the log distance between the transmitter and receiver, which captures the attenuation due to free space. Second-order models consider shadowing or slow fading, which captures the attenuation due to obstacles. Third-order models consider multipath components, or fast fading, which captures reflected and diffracted signals. For static transmitters, especially given a known map of the environment, data-driven methods can be used to fit accurate spatial models of signal strength prediction, and this is shown in prior work. For mobile robots operating in unknown environments, we investigate how the robot's onboard LiDAR, which is used to create partial maps, can inform signal strength prediction. The first contribution of this work is concerned with modeling the propagation environment between a transmitter and receiver, which depends on the geometries of the physical environment and the signal's characteristics, including the transmit power and frequency. From these, our model outputs salient features for propagation modeling. Beyond distance, these include whether there is line of sight, how much of the line of sight path is through occupied space or obstacles, and whether copies of the signal reflected off the ground or diffracted around a nearby object will cause constructive or destructive interference. So in a way, PropEM acts as an encoding layer between raw sensor data, which is these sparse 3D point clouds on the left, and a few key numbers for signal strength prediction on the right. To do this, PropEM internally builds and maintains a 3D occupancy grid used for ray tracing. The second contribution of this work is a thorough comparison of learned models, which use these features to accurately predict received signal strength. On the left, we show a snapshot of the performance of conventional models of signal propagation from the literature. True measurements are shown in blue. Overall, these achieve average errors between 6.5 and 12 dB. On the right, we introduce 5 fully connected neural networks, each which take a subset of the features encoded by PropEM and minimize the L2 loss between the predicted and measured attenuation. We observe that these models are better able to capture the data, and the richest of them, which we call NN-all, achieves an average error of only 3.73 dB. Given our interest in exploration, we then test these learned models in a new environment. Note that fitting the simpler models results in interpretable parameters. So we can immediately observe that the test environment is very different, with narrower corridors and more severe attenuation from obstacles. This demonstrates the need to update our learned models online by retraining periodically, while starting with the model trained offline prevents overfitting to the first few minutes of data. Relative to the baseline trained offline, our best performing neural network cuts the mean absolute error in half over the course of 1 hour of exploration with 6 robots. Additional results and discussion are included in the paper. To summarize, our approach uses 3D point clouds from the robot's onboard LiDAR to model how the environment will affect radio propagation, combines conventional signal propagation modeling and machine learning for accurate prediction, and updates online to adapt to new environments, which can even provide insight on the qualities of the environment itself. This inference is an interesting direction for future study. Again, my name is Lily. If you have any questions, feel free to get in touch. Thank you.
Is Lily online? Do we have any questions? We're trying to get Lily on the screen as well, so let's hope that works. Okay, then let me, oh, there we go.
Okay, cool. I have a question for the trajectory games paper. Did you guys find either the pursuer or the person fleeing, if any of them had any like dominant strategies at all?
Sorry, can you repeat that? Sorry.
Yeah, of course. Were there any dominant strategies for the pursuer or for the person being pursued?
So, like, you would very typically see that the evader, for the evader, it's very important to like randomize to like go either left or right. And you would very often see that if you have like a fast maneuver of like evading, you would sort of threaten the pursuer with maybe like decelerating and hiding in a corner. So that's like a very typical thing that we would see. Yeah. I'm not sure whether that answers your question.
Cool. Yeah, we can talk more in the post-session. Thank you.
I can't really see if there's anybody. Oh, there's somebody upstairs, I think. Yes.
Hello. Hopefully people can hear me. I had a question for Lillian about the radio frequency propagation work. I think this may be less relevant in the cave environment you were working in, but it seems like in many cases there are sort of non-geometric material properties that might be important for radio frequency path prediction. So like a drywall wall might be different than a brick wall in a way that's not purely a property of its geometry. Is that something that you think your method could sort of be extended to handle, or is that something you think would be relevant?
Yeah, that's a really good question. For our method, where it stands now, it's sort of taking an average case of the environment because we're updating those specific parameters the same way. But you could think of an extension where you also pass in like certain other features like just XYZ coordinates, and then maybe if you had more data with, you could train such that you are learning not just for this much obstacle density, I expect this much attenuation, but like for this much obstacle density, which happens to be in this part of the environment, I'm seeing different patterns there. But that is a really hard thing to measure because the sensors that we have on board were not giving us any information about how sort of opaque to RF signals the different obstacles were. So another thing you could do would be to have different sensors and try to use those measurements.
That makes a lot of sense. Thank you very much.
Okay, second question from up there.
This is for the bridging paper. So I wanted to know what role does the synchronization or of the sort of like the tensile interactions between the agents play in the success of the whole scheme? Like if they were all making decisions asynchronously, would the scheme also hold up?
Yeah, so at the moment they are, as you say, making decisions all at the same time. It's like a synchronous process. I would imagine that it wouldn't make too much difference if it was asynchronous, as long as the communication was like reliable between agents. They only need to kind of know vaguely where they are on the structure in order to operate properly, I think.
Okay, thank you.
Hi, Lily. Great talk. So during your talk, you focused mostly on like evaluating how well you can predict signal strength. And I wanted to know how much you've thought about like how that relates to tasks and like task performance, or what tasks can benefit most from better communication models?
Yeah, that's another good question. We mostly were looking at this for specific applications in which you want to, the robot's trying to make decisions about where to return to in the environment where they would have good signal strength. So like SNR, like raw SNR was the only metric that we were really interested in, and that was the main application that we considered. If you wanted to get sort of more broader system level metrics, it would be good to look at things like how much data capacity was, like how much data actually flowed over those links, latency, like there are other things that we could consider, but that's what we focused on for this work.
Thanks.
Okay, and then the very final question.
Just to follow up to the last question for the bridging paper, do you feel like your model could be extended to where a situation where you don't have communication between all of the agents or where you have lossy communication between the agents? For the bridging paper, for the bridging
Sorry,
agents.
I thought you were following up to that.
No,
Can you repeat the question, sorry?
Yeah, do you feel like your method, you said they needed to have good communication. Do you feel like it could be extended to a situation where you have lossy communication between the agents or where you don't have complete information from all of the agents involved?
Yeah, so there is quite a lot of communication, but it's all local in this case. So I would, again, we've not tried it, but I would suspect if one or two of the communications are wrong, like if an agent miscommunicates its force, I think the algorithm would still work because it's mostly probabilistic based. So agents don't go to like the exact best place. They like calculate a probability distribution of where they could go. So maybe if they go to like the third best one, it's still fine.
Cool, thank you very much.
Yeah. Good, then let's thank the speakers one more time.